In January 2005, NASA launched a unique space probe. Its goal was to discover where Earth's water originally came from. This probe, known as Deep Impact, traveled 27 crore kilometers to reach near a comet. Many secrets were hidden in this comet, secrets that had been searched for over centuries. It seems Earth was made especially for humans. Everything required for life, like water, food, and oxygen, is found here. There may or may not be any other such planet in the vast universe, but currently, Earth is the only place we know where humans can live unaided. But 5 billion years ago, Earth didn't even exist. The location where Earth and the entire solar system exist now was just a part of the edge of the Milky Way galaxy. Back then, instead of planets, there was a massive cloud made of mud and gases. So, how did this cloud turn into the planet we now call home? This massive dust and gas cloud is known as a molecular cloud. It contained particles like sand, silicon, and various metals, formed from the debris of dead stars. At the beginning of the universe, stars that burned all their fuel exploded, scattering their particles across the universe. Unlike the clouds we see in the sky, these molecular clouds were captured through the Hubble Space Telescope. Surprisingly, this particular cloud was about 100 light years across, meaning light would take 100 years to travel from one end to the other. To simplify, this cloud was 60 lakh times bigger than the distance between the Earth and the Sun. These clouds are the birthplace of new stars and planets, and the force responsible for this transformation is gravity. Gravity in space causes two objects to pull toward one another. The object with more mass pulls with greater force. Due to gravity, particles in the molecular cloud began sticking together. Larger particles attracted smaller ones, causing high-speed collisions, and those collisions generated heat and energy. The central part of the cloud began to rotate and heat up. Over millions of years, the core grew larger, rotated faster, and became even hotter, until it became a massive fireball, our Sun. The leftover cloud began orbiting the Sun, and from its particles and gases, the planets, moons, and life forms began to take shape. This process was once a mystery, but now we have clear evidence. The star formation theory was first introduced in the 1700s by German philosopher Immanuel Kant and French scientist Pierre Simonet, but back then, it was only a theory. From 1920 to 1950, as telescopes advanced, scientists began making observations, but they still couldn't see into these dense molecular clouds. It wasn't until the invention of radio and infrared telescopes between 1970 and 1980 that scientists could observe the insides of molecular clouds. These observations revealed that new stars are indeed born within these clouds, and planets are formed from the leftover dust and gas. But how does this process begin? Many ideas were discussed over the years, but the answer came from an experiment conducted in March 2003 on the International Space Station. Astronaut Don Pettit was experimenting with everyday items to study their behavior in space. He created water bubbles, dissolved substances in them, and even spun salt inside a plastic bag. Although the experiments had different objectives, his last experiment solved a major mystery. When the salt was placed in the bag and spun, the particles slowly began sticking to each other. In space, these particles naturally attract one another. Scientists believe the particles in the molecular cloud behaved similarly. They clumped together just like the salt particles did in Pettit's experiment. About 4.5 billion years ago, the dust particles started forming clumps. When the clump reached the size of a 1-kilometer mountain, its gravity increased enough to pull in more material, like a vacuum cleaner sucking in dust. This process continued for about 3 million years, forming around 20 small planets. Each was revolving around the Sun. Because these planets had become so large, their gravity pulled them into each other's paths. They began to collide, and with every collision, two smaller planets merged into one larger body. Eventually, where there were once 20 planets, only a few remained, including Venus, Mercury, Mars, and our Earth. But Earth at that time was not blue and full of life. It was a burning fireball due to intense collisions. Even if life had formed, it would have evaporated instantly. Earth needed to cool down before life could emerge, but until then, it had to survive its greatest threat, solar storms. Solar storms can severely damage a planet's atmosphere. They also strike other planets, making life there impossible. Even Mars, Earth's neighbor, was affected. Its atmosphere was damaged by solar radiation, reducing the chance for life. So how did Earth survive? The answer lies in the planet's core. As Earth's temperature rose, rocks and metals like iron and nickel melted and sank into the core. Because iron and nickel are heavy, they naturally settled in the center. Geophysicists explain that when molten iron rotates, it generates a magnetic field. Since Earth's core is rich in molten iron, it produces a strong magnetosphere, a field that protects the planet from harmful solar radiation. This magnetic field extends up to 370,000 kilometers on the side facing the Sun, almost reaching the Moon, and extends even farther on the dark side. That's why solar radiation gets deflected. At the poles, where the magnetic field is weaker, some radiation enters and creates beautiful displays, known as aurora borealis, northern lights, and aurora australis, southern lights. But these radiations are not strong enough to harm us. Still, early Earth was far from being life-ready. It had to endure one more massive event, a planetary collision. We learned about this in 1960 when NASA's Apollo missions began sending astronauts to the moon. Initially, scientists believed the moon was once part of Earth. When samples of moon rocks were brought back, they didn't match Earth rocks. They looked burnt. However, the oxygen isotopes matched, confirming the moon originated from Earth. So how did this happen? A Mars-sized planet named Theia collided with Earth during its early cooling phase. This violent impact released tremendous energy, and fragments of Earth and Theia were thrown into orbit, eventually forming the moon. In the beginning, the moon was much closer to Earth, about 15 times closer than it is now. Gradually, it's been drifting away at about 1.5 inches per year. This collision and the moon's formation were crucial. Scientists believe that without these events, life on Earth might never have begun. The collision caused Earth to tilt on its axis by 23.5 degrees. This tilt created seasons. As Earth revolves around the sun, different hemispheres get different amounts of sunlight, causing summer and winter cycles. Thanks to this tilt, we experience changing weather, enjoy various fruits and vegetables, and benefit from the rain cycle. The moon also influences ocean tides, which help spread nutrients across the sea, crucial for marine life. But these waves only matter if water exists on Earth. So where did that water come from? That's been one of science's biggest puzzles. To answer it, NASA launched the Deep Impact mission in January 2005. The probe was sent to a comet named Tempel 1, 270 million kilometers away. Attached to the probe was a 350-kilogram copper impactor, which was to crash into the comet. On July 4, 2005, it hit Tempel 1 at a speed of 38,100 kilometers per hour, creating a huge crater. The event was recorded by Deep Impact's radio telescope. The light emitted during the impact was analyzed using spectroscopy, revealing that Tempel 1 contained water ice. This proved that water exists inside comets in the distant asteroid belt. But how did this water reach Earth? Scientists believe that the mighty planet Jupiter is responsible. Jupiter's powerful gravity disrupted the orbits of comets, turning their circular paths into elliptical orbits, bringing them close to Earth. When comets crossed Earth's path, Earth's gravity pulled them in. Geologists now agree that Earth received water about 500 million years after it formed. Evidence comes from a mineral called zircon, which forms only in the presence of water. Zircon also contains uranium, which helps determine its age. All zircon samples on Earth date back to 4 billion years ago, half a billion years after Earth's formation. From the birth of the Earth in a molecular cloud, to the Theia collision, to the moon's formation, to the delivery of water by comets influenced by Jupiter, every event helped make Earth suitable for life. The planet's temperature had cooled to nearly 100 degrees Celsius, but oxygen, the final ingredient for life, was still missing. So now it's your turn. Tell us in the comments, how do you think oxygen came into Earth's atmosphere? We hope you enjoyed this Fact Black Hole video. Don't forget to like, share, and leave your thoughts. Thanks for all your love. See you in the next amazing episode.